Hello and welcome to the Maths 2 component of the online course on data science. In this video, we are going to talk about inner products and norms on a vector space. This is linked to our previous video, which was on length, angles and dot products. So, we will see that the notion of an inner product generalizes what is a dot product, and the notion of a norm generalizes what is the length. So, the point here is that we can do this for any vector space. So, let us start by defining what is an inner product. So, an inner product on a vector space V is a function which takes two vectors as input. So, that is why the dot comma dot. So, in place of the dots you will have vectors. So, it is a function from V cross V to R. So, it produces a real number for each pair of vectors. It produces a real number, and it satisfies the following. So, if you apply this to V comma V, that means you take just one vector and you think of it as the tuple V comma V, then the inner product of V with itself, that is how we will say V comma V, this angle brackets, this must be positive, strictly greater than 0. If V is non-zero, and it will be 0 precisely when V is equal to 0. Okay. And then you have these three things which I have put together because they are called this is saying that it is bilinear. Okay. So, these three things say it is bilinear. So, V1 plus V2 is comma V3 is V1 comma V3 plus V2 comma V3. And V1 comma V2 is V2 comma V1, and C times V1 comma V2 is C times V1 comma V2, which because of your previous thing can be written also as V1 comma C times V2, where C here is a real number, it is a scalar. Okay. So, I will also point out that using these two we can get that V1 comma V2 plus V3 is equal to V1 comma V2 plus V1 comma V3, right, because V1 comma V2 plus V3 is V2 plus V3 comma V1, which is then V2 comma V1 plus V3 comma V1, and then you can flip those again to the other side. Okay. So, now these three together are what is called bilinear. So, this is a bilinear map, the first and third. So, a vector space together with an inner product is called an inner product space. So, I will underline this. This is called an inner product space. This is a definition, right, and maybe I will just put in the conclusions we drew. So, the conclusions we drew before were that so, first of all, here this is not a conclusion, this is a hypothesis. C is a scalar, and the conclusion out of this was that V1 comma V2 plus V3 is V1 comma V2 plus V1 comma V3. Okay. So, the dot product is an example of an inner product. This is what I started with. So, recall that the dot product of U and V in Rn is U dot V is U1 V1 plus U2 V2 plus UN Vn. I apologize for this ugly look in full stop, which should have been here, and this yields a function which is given by U comma V is U dot V, yeah, angle brackets U comma V is U dot V. So, why is this inner product? So, we have to verify the the four axioms we had. So, we know already that if U comma U is, so this is U1 squared plus U2 squared plus UN squared. For real numbers, squares must be positive, sum of squares is positive. So, that means this is greater than 0 if U is not 0, and this is equal to 0 exactly when each Ui is 0. So, Ui is 0 for all I, which happens precisely when U is 0. So, we have proved the first one, and the other three just follow from the form of this equation. So, if you have U plus U prime dot v, you can check that this is actually u dot v plus u prime dot v, and similarly if you have u dot v, this is same as v dot u. That is clear from the equation, because real numbers you can they commute under multiplication, and then clearly if you have cu dot v, this is c times u dot v, because c multiplies into each component. So, for each component you will have it over there, and then you can take it out. So, this completes the proof that this is indeed a inner product. So, the dot product is an inner product. So, let us now look at an example of an inner product on R2, which is this is not the standard inner product that we saw, the dot product that we saw earlier. This is a slightly different example. So, here is the definition: u comma v is x1 y1 minus x1 y2 minus x2 y1 plus 2 times x2 y2. So, where u is x1, this is a typo here. So, u here is x1 comma x2 I think, and v is y1 comma y2. Okay. So, the standard inner product that we saw was, so if you do u dot v is x1 y1 plus x2 y2, right. So, sorry, in terms of is x1 y1 plus x2 y2. The inner product here is slightly different, as you can see. So, why is this an inner product? How do I prove that? So, this is proved by looking at the following. If you look at this expression, you can write down a matrix for this expression. So, you have x1 x2, and then you have y1 y2, and then let us see. So, you have x1 y1, the coefficient is 1, x1 y2, the coefficient is minus 1. So, I believe there should be minus 1 here, and then this is minus 1, and then this is 2. Okay, so, if you multiply this, let us see what we get. You get exactly, so the first term is x1 minus x2, the second term is minus x1 plus 2 times x2 times y1 y2, and if you work out what this is x1 y1 minus x2 y1 minus y2 x1 plus 2 times x2 y2. So, this is exactly what we have up here, right. This expression and this expression are the same. So, this is a different expression from the inner product, which is x1 y1 plus x2 y2. And now, how do I use this matrix form to conclude that it is an inner product? So, the reason so I can use the matrix form to conclude that it is the inner product, because the bilinearity part follows directly, and the symmetry part follows because this is a symmetric matrix. So, if I want to do y1 y2 comma x1 x2, then you can see that this is exactly writing y1 y2 here, writing the same matrix here and x1 x2, but this is a real number. So, I can, so this is the same as its transpose, this is the same thing transpose, and if you do the transpose, you will get this, because the matrix in the middle is a symmetric matrix. So, it transposes itself. Okay. So, that is why it is symmetric, that is the second property. And then bilinearity is because matrix multiplication respects addition, right. So, if you have, so it distributes over addition. So, if you have x1 x2, let us say plus x1 prime x2 prime, then over here you will that will distribute and it will give you what you want. That is the first thing. And then c times x1 x2, again because constants come out of matrix multiplication, it will follow from there. So, I will urge you to check that fact, because these two expressions are the same. So, the key point here is these two expressions here are the same. So, maybe I will draw that better. These two expressions are the same. Okay. So, you can check it from there. So, the only remaining thing is that this is always positive. So if you put x1 x2 in place of y1 y2, what do you get? So you get x1 squared minus x1 x2 minus or rather plus x1 x2, so that is 2 times x1 x2 plus 2 times x2 squared. So this is x1 squared minus 2 times x1 x2 plus 2 times x2 squared, and you can write this as x1 minus x2 squared plus x2 squared, right. So this is the sum of squares. Again, it must be positive. If it is equal to 0, then both the terms which are squares are 0. That means x1 minus x2 is 0 and x2 is 0. Once x2 is 0, x1 must be 0. So both x1 and x2 are 0. So that tells us that it is 0 exactly when u is 0. So this proves that it is an inner product on R2. Let's define what is a norm. So a norm on a vector space is a function. It's indicated by that double lines, and we have seen these double lines in the previous video. X goes to norm x, which satisfies the following conditions. So norm of x plus y is less than or equal to the norm of x plus norm of y. Norm of c times x is absolute value of c times norm of x. So remember, in the previous video this norm was supposed to represent length. So since it represents length, it better be positive, and so if you scale it, the length better remain positive, right. That's what is being reflected here. So positivity is coming in the third axiom. Norm of x is always greater than 0, and it's 0 precisely when we are dealing with the 0 vector, if and only if the vector x is 0. Fine. So let's recall the length of a vector. This is the comment I made in the previous slide. U, it's given by this expression root of x1 squared plus x2 squared plus xn squared, and this is actually a norm. So we have to say that the 3 previous conditions are satisfied. As I said, if you multiply this by c, this is clearly root of c squared x1 squared plus c squared x2 squared plus c squared xn squared, and the c comes out but with an absolute value, and the remaining part is norm of u, length of u. Sorry, this should have been 2 bars. Let's see when this is 0. This is 0. We have actually checked this. So the length is 0 exactly when u is 0. This is something we know, which leaves us with the triangle inequality. Namely, if you take 2 vectors u plus v, then you compute their sum. So this is root of x1 plus y1 squared plus x2 plus y2 squared plus xn plus yn squared, and on the other hand we have norm of u plus norm of v, which is x1 root x1 squared up to xn squared. This is root y1 squared plus all the way up to yn squared. So I want to say that this sum is less than or equal to that sum, and this is something that we know is true, and I'll maybe not do a proof of this, right. So what you can do is you can square both sides. If you square both sides, you will get x1 plus y1 squared plus all the way up to xn plus yn squared. This side you get x1 squared plus all the way up to xn squared plus y1 squared all the way up to yn squared, and then plus 2 times this this root, and then y1 squared plus all the way up to yn squared. And then, so to compare these, so I want to compare these. So to compare these, you can expand the brackets. If you expand the brackets and you cancel off these square terms, you are going to have to compare 2 times x1 y1 plus 2 times x2 y2 plus 2 times xn yn with this side. And now I will leave it at this point to So you can cancel off the 2's as well. So you have to compare this term with this term here, and yeah, I will maybe not get into a proof that this is actually this is less than or equal to that. It's a very something you can do. Okay, so the length function is a norm on Rn. So let's look at a norm on Rn, which is different from the length function. Namely, you can take the absolute values of the coordinates. So norm of u 1. So this 1 is supposed to I think this 1 has not come out the way I intended it to be. This should have been the subscript, but it did not come out as far as I wanted it. Anyway, so define norm of u to be this, the absolute value of x1 plus absolute value of x2 plus absolute value of xn, then this is a norm. So let's check that this is a norm. So first of all, I want to check that if norm u1 is 0, this is the third axiom. What happens? Well, this is a sum of non-negative integers. So this happens exactly when each xi is 0 in absolute value, which is exactly happening when xi is 0 for all I. So for all I, which is exactly saying that u is equal to 0. So if this norm is 0, if this function is 0 on u, then u better be 0, and of course if u is 0, then the function is 0. So this is one thing that we have checked. The other is if you multiply this by a constant c, by a scalar, what happens? Well, each term is multiplied by c. So I get this expression, excuse me, I should have put in the dots, yeah, this expression, and I can take my c out common, because remember that the absolute value of two numbers multiplied is the absolute value of each multiplied. So you take c out, absolute value of c out common, and you get x1 plus x2, all these in absolute value. So absolute value of x1 plus absolute value of x2 all the way up to n, which is exactly what is the definition of the norm here. So c times this function. So this gives you one more thing, and then the last one that we have to do is the triangle inequality, which is saying that if you have u plus v, you take this. Well, let's write that down. That's x1 plus y1 plus x2 plus y2 plus xn plus yn, where xi's are the coordinates of u, yi's are the coordinates of v. But we know that this is less than or equal to x1 plus y1, this is less than or equal to x2 plus y2, and then if you rearrange all these terms, you get that this is u1 plus v1. So this tells you that it is a norm. Okay, so it's a fairly simple check that it's a norm. So finally, let's explore the relation between the inner product and the norm. So suppose you have V, which is an inner product space. So it has an inner product which we have represented by these angled brackets. Let's define this function. So this function is norm of V is equal to square root of the inner product of V with itself. Then the claim is that this is the norm on V. Let's work this out, why this is the norm. So first of all, norm of V is 0. This happens exactly when the square root of the inner product of V with itself is 0, which happens precisely when the inner product itself is 0. But remember, it's an inner product. This happens precisely when V is 0. So I want to prove that this is always positive if V is non-zero. But remember that V comma V is, so if V is not equal to 0, V comma V is greater than 0, that means square root of V comma V is strictly greater than, we are always looking at the positive square root, which means norm of V is strictly greater than 0. Okay, so the positive, non-negative and positive part is proved, that axiom is proved. So the other two axioms are the triangle inequality, and if you multiply a scalar, what happens? Let us look at scalar. So for the scalar, so we have c times v. By definition, this is cv comma cv, but as we know, c comes out. So this is root of c. So it comes out of the first one and it comes out of the second one. So c times c, excuse me, this is norm of v, inner product of v comma v. So this is root of c squared root of v comma v. The second part is exactly the norm of v, and the first part is mod of, meaning the absolute value of c, because you are taking root of c squared. So if c is a negative number, after taking square root you always look at the positive part, right. So it is the absolute value of c times norm of v. So this is the another one of the axioms, and finally we have if you have v plus w, by definition this is v plus w comma v plus w square root, and this is so you have 4 terms, right. You have v comma w plus v comma w comma v plus w comma w, which if you rewrite, this is v comma v, and this is remember it is a inner product. So it is so the first, we got the first thing by bilinearity, and then because it is symmetric, we get this is 2 times v comma w plus w comma w. So let us square this. So if you square this, you get v comma v plus 2 times the inner product plus w comma w, but this is exactly norm of v squared plus norm of w squared plus 2 times v comma w, and this is less than or equal to norm of v squared plus norm of w squared plus 2 times norm of v norm of w. So this needs a little bit of work, and then what you will get is that this is norm of v plus norm of w the whole squared, right. So we have proved that norm of v plus w the whole squared is norm of v plus norm of w is less than or equal to norm of v plus norm of w the whole squared. Yeah, the only thing missing here is why is this thing less than or equal to this thing here. So that needs a little bit of work, which I will skip for now. So I guess this tells you the relation between inner products and norms. So the main point here is that once you have an inner product, it induces a norm. This is what you have to keep in mind. Thank you.